All right, so inverse logarithms, or sorry, inverse functions and logarithms. When we talk about inverses, we are going to denote it with a little -1 by the f. This does not mean I'm raising it to the power of -1, just to inverse of f. And essentially what we are doing when we are doing inverses is we are switching the positions of x and y. So x and y are swapping up when we take the inverse. So for example, if there is a function where I put in an x and it gives me a y of 550, and then I do the inverse function of 550, I should get back what the swap. Okay, so if the function takes the 6 and gives me a 550, then the inverse function will take the 550 and give me that. A function is called one-to-one. We would have done this in Calc12. A function is called one-to-one if any output f means it cannot equal any other output f of x2, where you have x1 and x2 are different. So let me put this in some English words. Each unique test means that no x1 equals any other x2. Any two x's cannot be the same. So each unique test gives a unique y. Remember, y is f of x. So if I have a for any unique x1, it equals no other x2. And when I put it into the function cannot equal itself. All my x's are unique and all my y's are unique. Anybody remember this test? Horizontal line test and vertical line test. So what is the two? What are some key points? 1, 1, 0 times. Okay, a vertical line test is where I'm checking the graph vertically and making sure that no matter how many of these pink lines I draw, they only intersect the graph at one point. This tells me that I have the function. Because it passes vertical line test. Check. All my pink lines only cross the boundary of the black line one time. Now, if it's a one-to-one function, then I can also do the horizontal line test. If you draw horizontal lines across the graph. And again, I'm only comparing it to the original, the black. Okay. Black line was there. It's only touching the black graph one time. So if it passes the vertical test and it passes the horizontal test, then you have a 1, 2, 1 function. 1, 2, 1 function. So x cubed is a one-to-one function. What are some key points on the next grade? 0, 1, 1. 1, 1. 2, 4. Does it pass vertical line test? LP test. Does it pass horizontal. So this is a function, but it is not function. Remember seeing this at some place? Some no, some no. Okay, let's see how this affects our domain. If f, the function, is one-to-one function with the domain and range A and B, then the inverse of the function has the same domain. Okay, so I'm going to zoom in on my x cubed here. I'm going to erase all my x. What this is saying is, because this is a one-to-one function, what is the domain and range of this function? Right, so we have all reals, and what about the y? Okay, so we have all reals, all reals. We know this is a one-to-one. So that means the inverse function for x will also be all reals. So we have the same. These are 2 points. Because we are swapping spots between x and y, then the domain of f inverse equals the range of f, because we're swapping the positions of f. So on the original graph, we have a domain of something. It is now the range of its inverse. Okay, the range of the inverse, the domain of the. Okay. Quick step. You are told that when the function takes a 1, it spits out a 5. The function takes an x of 3, it gives a y of 7. When it takes an 8, it gives a 10. So if I were to do the inverse, and the inverse takes a 7, what's the output? 2. Then 1, and okay, so we're just swapping. Okay, to write the inverse function of a one-to-one function, we write, okay, and this is where I start disagreeing with our workbook. In the workbook, it says, change the y to an x, change the x to the y, and then solve for y. Then you'll have the inverse. So change the x and y, and then solve the inverse. So this is what it's asked. Based on this function, remember that this is our output. This represents the y. So I'm going to write y equals x cubed. And the workbook is telling us, put the x here, put the y here, and then solve the y. Can we do this? Yeah. What's my first step? Minus 2. Minus 2. Okay. I don't like this one. Not because it's wrong, it is correct. If you do something, you're going to get the right answer. That's fine. However, I have a lot of students who, when we start doing more complex equations and stopping them and doing applications with them, they get confused as to where is the original function. This one. What I like to do is this. Take what you got, solve for it. Take what you got from them. I minus 2 is this. Cube root I minus 2. Okay. The reason I do it this way in my brain, I can see that this is the inverse and that this is the original. Right? And then when I go to graph it, I can say f Green is an inverse. So we're trading the two classes of this. What I'm doing is I'm skipping this step here. I'm just solving for the x, inverting it, and then I'm going to write it as this. The inverse function is x minus 2. I don't like when we put the y here because it really confuses the original and the inverse function. So if you're going to swap it first and solve for y, or if you leave it as is and solve for x, just make sure in your final statement you are writing it as an inverse. And because we are graphing this, we want the variable to be x, but we need to make sure that we are identifying that this is. Okay, so there's many ways you can do it, as long as you differentiate what is the original function, what is the new function. Okay, what is the domain of the original? What is the range of these? X cubed plus 2. 7, all of it. 5, all of it. Okay. We are reflecting this over the x, y line. I'm going to do a visual demonstration. You don't need to flip back with me. But just watch the screen for a second. Here's the x cubed line, right? What does y equal x look like? Straight line, starting at 0, 0, with a slope of 1, yeah? So when we take the inverse, what we are doing is we are doing a reflection over that diagonal line. So we're folding the graph diagonally over that line and reflecting it. So then this 0, 0, 1, 1, but now the graph is going to go this way. 0, 0, 1, 1, now the graph is going this way. You see how that is a square root function or a cube root function? Right? So a root function is when we reflect a square function or a cube function or whatever power function over that line. And you can do it with any kind of function. I just wanted to do it here so you can see it's a graph that you know and you can recognize it. Okay? So here, when we flip it, or sorry, invert it, what is the domain and range here? So if it is a one-to-one function, the domain and range are inverted, but they're going to be the same. Meaning if the domain is all real, the range is all real. Range is all real. This is not true for all functions, especially if they're not one-to-one. Okay, so you've got to be careful with these. Let's go with example 4. I want to graph the original first. So let's take f of x. You want to call it y for now, just for simplicity. I have an x that does not have a coefficient of positive 1. I'm going to factor out and make it. What are the transformations? Reflection on the y-axis and left. Okay. A basic y equals square root x would look like this. 0 on. What does this function look like? Remember that we have to do this in order as what am I doing first? Reflection, so I'm flipping it backwards like that, and then left 1. So this function is a So this is f of x, the green. Now, if I were to invert it, let me draw my inverting line. So 1, 1, here it is. Can you do this visually? If I fold this graph over, what does f to the negative 1? Where is this quantitative? So negative 1. This quantitative. What's the coordinate right now? Right now it's at -2, +1. We have one switching. We're switching the positions of x and y. This is at -5, +2. Where is it now? Okay. Okay, so we just folded it over the two lines. Okay, logarithmic functions are inverse functions to exponential. Okay, this right here needs to commit to memory. Okay, log base a of x equals y. The inverse of it is base a to the power y to x. Okay, so the way that I remember this kind of thing is by saying the base of the x, the base of the log is the base of the exponential. Base is base. Okay? And then whatever is inside the log is my answer. Whatever's on the other side is my exponential. Not really a great way to remember that part, but I just remember the base part. I erase all of this. In my head, what I'm doing is I'm taking this base, putting it here, pushing that log. Log go away, and then I'm left with an x on the side, a base a to the power y. Those are inverses that we said. Okay, some other laws that we need to remember. Do we remember this from last night? Good. Okay, so again, key point here is that the base must be the same. These rules always apply to the same base because remember these are like exponentials, like exponents. We have x to the a times x to the b. This is like saying x to the a plus b. But if I have x to the a times y to the b, can't do that rule because the base is not, right? It's really important to remember the bases must be the same in order for these. All right, let's do some examples. Let's refresh our memory. Can we evaluate these? Can we simplify them? Log base 2 over 5. So this is log base 2 of 2. Just for how did we get there? Right, this is log base 2 to the power, of 2 to the power 4. Right? And if you have the same base, have that here somewhere. Can we add this rule? 4. Log base a. Log. Oh, sorry. they're combining these two things, right? The exponent becomes a coefficient, and if you have the same base as the one. So we will. Okay, so we do the next one. Log of 100. 2, because what? Power 2, right? Whenever we don't see the base on the log, we assume it's a 10. Okay, next one. This is like 2 squared. Like 2 log 3 comes to 1. Do you remember doing this? Wonderful. Okay, we're going to do exactly the same thing, but with lawn for now. Lawn. This is the natural log. The only difference is the base is the letter E, but all the rules still apply the same way. Okay, so ln x is the inverse of e to the y, because it's like log base e. Okay, 2 point something is in our last one. Okay, let's do this example. If ln of x is 5, what is x? So ln of x equals 5. How can I rewrite it? The power of 5. Right? And again, if you didn't follow that, this is the same thing as saying log base e x equals 5. I'm taking the base, moving it over here, so I get x equals e. If I'm following the same log rules, but we're using a base of a natural number e, you need to throw that into your calculator. This is approximately 148.4 ... E is not a rational number, so it's like pi, it's on forever. You need it in exact form. This is pi. Okay, let's start solving that. E to the power 5 minus 3x equals 10. What would I do? On both sides. Ln e to the 5 minus 3x equals ln 10. Is a number. You're not scared of it. Okay? What happens on the left side? The ln and the e cancel out, and left is 5 minus 2x equals ln 10. X equals ln 10 minus 5. X equals ln 10 minus 5 over. You check that in your calculator. Not going to worry about it, right? Remember that when we have a fraction that has more than one term in the numerator denominator, please make sure you're adding brackets when you put that into your calculator. The calculators are not very bright. Okay, so this will be approximately 0.9-ish. Okay. Expressed as a single logarithm means let's use our log rules to make this one thing. What would I do? I see an ugly number here. What does that mean? Oh, yes. Okay, so this is ln a plus ln b to the power of 1 over 2. Then I do what? Ln. Perfect. There it is. Okay, when we are combining things, please make sure to remember coefficients are exponents. That first, and then talking again. I will do a proof for you another day. I want to do more examples today. Example 5, can you evaluate? Now I want calculator question. Log base 8 to 5. Can you show me how I could rewrite this? Log 5 over log 8. This is how we're going to use this for our calculator. Our calculators do not give us the option to do this. We cannot change the base of the log function. So we can't want to do that. So we are going to change base of the 10, 5. Say that again. You can use it. Okay, what did you get? 773,976. 0. Stop it. Okay. Remember the math question if you watch last lesson. In the last lesson, we did an exponential growth and decay question. When we do exponential growth, we measure the mass as a function of time, right? So this is replacing what used to be f of x. Now I'm specifying my f is measuring mass, not my variable is time. Okay. Our original mass is 24 milligrams. We are looking at the half-life. And we can measure our time divided by the half-life. Strontium 90 is 5. This is from the last one. So know that. No. Okay. So find the inverse of this function. Notice how they wrote it. I said that 1 over 2 is to the power of t25. They wrote 2 to the power of negative t25. Is that the same thing? Okay. Find the inverse. Remember, this inverse is an exponential. We're going to use 1 log 2. So m equals 24 2 to the power of negative 5. What's my first inverse? Want to get to 2. I could log both sides, but I want to do something else. Yeah, let's divide by 24 to get rid of this coefficient. Now I'm going to log it. For log. Okay, so this is on m over 24 equals. How do I write the right side if I log? 25, right? Exponents become coefficients on. What's my next thing? Times 25. Can I do negative 25? There. And okay, so now if you knew the mass, the resulting mass, you could, from the half-life formula, figure out how much time it took for a sample to be. So T equals negative on and all over. So if you started with 24 milligrams of strontium 90, and it's now reduced to 5 milligrams of strontium 90. How much time has passed since together? How do you do that? 5. Tuck it in your calculator with you. What's the meaning? Okay. Do we remember what? Because this is exponential decay, you could ln over log. You could use a log. The ln of this is essentially using t out of the base, and what video we have those easy as our t point is equal 1, whereas if you use a log of a different base, that would a slope of t calculus is also. In the last video, could use log. Okay. I'm going to assume that we haven't watched last week's video or last video, so I'm going to do a quick demo here. E to the x is an exponential growth where the key point is 1, 0. It goes up like this, like this. Ln of x is the inverse to this. So when I have here is my y equals x prime. Okay. When I have the inverse of this, in order to graph the ln function, I have to reflect it over the diagonal. So my key point of 0, 1 is now going to be here at 1, 0. And this graph is going to go like this. Okay, now Px has a horizontal asymptote at y equals 0. Inversely, now ln x has a vertical asymptote at x. Okay, we have now the base for our ln x graph. I'm going to erase this E graph because for this question, I want you to transform the ln graph. Okay, here's what the base of the ln graph looks like. Take a look at this transformation. What am I doing here? Down 1. Right. Okay, so I'm taking my 2 points down 1, right, 2. Here is my y graph. Okay, where's my vertical asymptote? How are we feeling with it? Good. I'm going to stop here because of time. I'm going to finish the trigonometric section in a shorter video.